It will be Cascadia that will trigger the first real megaquake in the United States. Megathrust earthquakes, media sensationalism, or real threat? The term megathrust earthquake refers to exceptionally powerful earthquakes with a magnitude of at least 8.5 on the Richter scale. While the term hasn't yet found a precise scientific or formal definition, it has become associated with extreme and rare events, especially after the disasters in Sumatra in 2004 and Japan in 2011. These quakes typically occur near the Pacific Ring of Fire and are caused by the interaction between two continental tectonic plates, often followed by violent tsunamis. But if megathrust earthquakes are indeed different from normal earthquakes, what are the distinguishing characteristics? And more importantly, can these characteristics provide clues about when and how these quakes will occur? In this spectacular video, we will try to answer all these questions and highlight the most at-risk areas for megathrust earthquakes on our planet, without hiding the fact that one of the regions that will eventually be struck by one of these events is in North America, Cascadia, the most at-risk region in the entire United States. We all know, either from direct experience or from news reports, that a magnitude 6 earthquake is enough to cause enormous damage and thousands of casualties. But if a non-destructive quake can have such catastrophic events, it's important to know that there are places where our planet can do even worse. We're talking about megathrust earthquakes. These seismic events can permanently alter landscapes and trigger disastrous tsunamis, causing hundreds of thousands of deaths. Megathrust earthquakes are almost exclusive to the coastal areas of the Pacific and Indian Oceans, regions also largely responsible for the volcanic activity associated with the Pacific Ring of Fire. However, it might now be easier to predict when the next megathrust earthquake could strike. A study published in Science identifies specific geological features at the meeting points of tectonic plates that make these colossal seismic events more likely. This could help authorities improve monitoring and risk prevention programs. All megathrust earthquakes originate in subduction zones, areas of the Earth's crust where one tectonic plate slides beneath another. This process is hindered by friction between the rocks, which can block the movement of the plates for millennia, accumulating enormous amounts of energy that are eventually released in cataclysmic earthquakes. Such zones are not rare, which is why seismologists and geologists have been trying for years to identify the most at-risk areas. One of the most common theories suggested that megathrust earthquakes were more likely in areas with fast plate convergence and when the subducting plate is relatively young. However, two of the most dramatic megathrust earthquakes in recent decades have disproved both possibilities. The 2004 Indian Ocean earthquake, which caused a tsunami with 30-meter or 98-foot waves and over 230,000 deaths, originated in an area where plate movement is relatively slow, not exceeding 3 to 4 centimeters or 1.2 to 1.6 inches per year. In the case of the 2011 Sendai and Tohoku earthquake, which caused the Fukushima nuclear disaster and over 15,000 deaths, the Pacific plate subducting under Japan is considered relatively old at 120 million years. In search of a new theory to predict the most at-risk areas, the authors of a new study, a team of American and French researchers, decided to study a different parameter of subduction zones, their geometry. They correlated the curvature of the fault line with the magnitude of past earthquakes. They discovered that the two parameters are inversely proportional. The straighter the contact line, the more powerful the earthquakes. Further analysis showed that a curved contact zone produces more frequent but less catastrophic earthquakes. The explanation lies in the energy accumulation capacity of subduction zones. A flat subduction zone accumulates energy homogeneously and tends to release it all at once, producing more powerful earthquakes. In contrast, a curved area accumulates energy more heterogeneously, with different points releasing energy at different times, resulting in more frequent but less powerful earthquakes. Based on these findings, researchers have calculated which known at-risk areas are most likely to experience the next megathrust earthquake. Here's a quick overview, considering that the largest possible earthquakes are estimated to have magnitudes between 10 and 11. These could likely be caused by a combination rupture of the Japan Trench and the Kuril-Kamchatka Trench, or individually by the Aleutian Trench or the Peru-Chile Trench. The largest recorded megathrust earthquake was the 1960 Valdivia earthquake, estimated between magnitudes 9.4 and 9.6, with its epicenter off the coast of Chile, where the Nazca Plate subducts under the South American Plate. Indian Ocean region. The Sunda megathrust, responsible for the 2004 earthquake and tsunami, is active where the Indo-Australian Plate subducts under the Eurasian Plate, along a 5,500-kilometer or 3,400-mile fault line. This uninterrupted chain stretches from the coasts of Myanmar, Sumatra, Java, and Bali, off to the northwest coast of Australia. Here, megathrust earthquakes exceeding magnitude 9 are likely. In the South China Sea, the Manila Trench can produce earthquakes of magnitude 9.2 or higher. Japanese Archipelago. Japan is highly vulnerable to megathrust earthquakes, particularly along the Nankai Trough. This 800-kilometer or 500-mile-long submarine trench extends from Shizuoka, west of Tokyo, to the island of Kyushu. It is a subduction zone where two tectonic plates converge in the Pacific Ocean. Historical records indicate that the Nankai Trough has experienced a major earthquake of magnitude 8 or 9 on the Richter scale every 1 or 2 centuries. According to Kobe University, there is a 70 to 80% chance that another such earthquake will occur within the next 30 years. The potential damage from this event is expected to be significantly greater than the 2011 Great East Japan earthquake. South American Pacific Coast. Located on the western edge of the South American Plate, Chile is frequently hit by large-scale earthquakes, including megathrust events. The country's proximity to the Peru-Chile subduction zone, one of the most active in the world, makes it particularly vulnerable to these seismic events. New Zealand. New Zealand is situated on the boundary between the Pacific and Australian plates, known as the Haiku-Rangi subduction zone. This geological feature makes the country susceptible to megathrust earthquakes, which can cause devastating tsunamis. The most recent quake in 2016 measured magnitude 7.5 and caused a tsunami with 2.5-meter or 8.2-foot waves and a lateral shift of 1.2 meters or 3.9 feet in part of the South Island. Caribbean Sea. A megathrust earthquake could also occur in the Lesser Antilles subduction zone, with a maximum magnitude of 9.3 or potentially even 10.3, according to recent assessments. This is the highest value among those predicted as possible on our planet. Okay, but how's North America doing? Are there any threats of megathrust earthquakes? Well, everyone knows about the San Andreas Fault, where the Pacific and North American plates slide past each other, running through densely populated areas of California. However, other faults also threaten the Golden State, such as the Hayward Fault on the east side of San Francisco Bay, and another fault discovered only after causing the 1994 Northridge earthquake. While the risk is not minimal, everything we know about earthquakes suggests that the Megaquake phenomena does not apply to the San Andreas Fault, which at most can produce a magnitude 8 earthquake. That's significant, but it won't be a megaquake, and there won't be any tsunamis. Alaska. The situation in Alaska is very different. It is the region with the highest number of recorded earthquakes in the United States and has experienced the most destructive seismic events in the country. Since 1900, Alaska has averaged one great earthquake, magnitude 8 or higher, every 13 years, one magnitude 7 to 8 earthquake every year, 6 magnitude 6 to 7 earthquakes per year, 45 magnitude 5 to 6 earthquakes per year, 320 magnitude 4 to 5 earthquakes per year, an average of 1,000 earthquakes each month. The last great earthquake in 1964, with a magnitude of 9.2, destroyed several towns and heavily damaged Anchorage. Alaska's saving grace is its much lower population density compared to California and the Pacific Northwest. However, the state's population has more than doubled since 1964, and there are now significant infrastructures like the Alaska Pipeline that weren't there before. Cascadia, the real danger. When it comes to earthquakes in America, people often ask, which city will the San Andreas Fault destroy first? San Francisco or Los Angeles? But if by the big one they mean the earthquake that will cause chaos over the widest geographic area, destroy the most critical infrastructure, and send tsunamis across the Pacific causing economic havoc for a decade or more, then the seismic demon to blame wouldn't be the San Andreas Fault. It would be Cascadia. When first discovered, many scientists thought the Cascadia Fault couldn't generate gigantic earthquakes. Now, they know they were wrong. They simply hadn't looked far enough into the past. Cascadia. The name Cascadia refers to the volcanic Cascade Range, and the fault extends inland and parallel to the coast for a length similar to the fault itself. This entire region is now believed to be capable of producing magnitude 8 or 9 earthquakes, as devastating as those off Indonesia in 2004 and Japan in 2011. The Cascadia subduction zone is where the Juan de Fuca and Gorda plates are colliding with the North American plate, sliding beneath it along a 1,200-kilometer or 750-mile front located 200 kilometers or 124 miles off the coast. The plates move very slowly but continuously towards each other, but are currently locked at the contact points. Eventually, the accumulated energy from the collision will surpass the frictional resistance, leading to what will likely be called the greatest natural disaster in North American history. Terrifying, right? But how can we be so sure about this? And why is there so little discussion about this impending catastrophe? There are many reasons, ranging from the media's focus on Hollywood's versions of the ultimate cataclysm, like the one that destroys the iconic city of Los Angeles, to the cultural isolation of wild regions like Oregon and the Canadian border. Hey guys, just a moment before we continue. Be sure to join the Insane Curiosity channel. Click on the bell, you'll help us to make products of even higher quality. Up until 40 years ago, no one even knew the Cascadia subduction zone existed. The last major earthquake in that area occurred several hundred years ago, before the Pacific coast was colonized by Europeans. Those lands were inhabited by Native Americans who, not having a written language, left no written record of that earthquake. Without clear evidence of a previous cataclysm and with nature quickly healing its wounds, the settlers saw the value of the area as fertile, temperate, and seemingly benign, and claimed it without realizing its danger. From then until today, Cascadia has been classified as the quietest subduction zone in the world. Along the fault segment, geologists couldn't find any evidence of major earthquakes in all of recorded history, meaning the 140 years since white settlers arrived in the Pacific Northwest and began keeping records. For unknown reasons, it seems to be a special case. The system was thought to be aseismic, essentially earthquake-free and harmless. In the 1970s, several competing theories emerged to explain Cascadia's seismic silence. One possibility was that the Juan de Fuca plate had changed direction, slightly rotating due to the movement of the two larger plates on either side. This would have reduced the eastward movement under North America and thus reduced the accumulation of seismic stress. Another possibility was that the angle of the descending plate directed eastward was too low to accumulate the type of friction needed to cause large earthquakes. But the third possibility was decidedly frightening. In this interpretation, the silence along the fault was simply a menacing pause. It could be that these two large slabs of the Earth's crust were stuck against each other and had been for a long time, locked together by friction for hundreds of years, much longer than all of recorded history. If true, they would be accumulating the kind of stress and tension that only a monstrous earthquake could relieve. But if that was the case, and if the fault was active, why were there no signs of past major earthquakes? The smoking gun for solving the case finally came from Japan, where many documents were discovered describing an immense wave that devastated the coast in 1700. That wave was clearly a tsunami, but its origin was unknown, so much so that it was referred to in ancient chronicles as the orphan tsunami, meaning it had no apparent cause. A few years later, in 1996, it was proven that the tsunami was caused by a magnitude 9.0 earthquake that struck North America on January 26, 1700. Thanks to this evidence, it was discovered that some Native American tribes had also preserved and passed down the memory of that event. There were stories referring to the earth shaking or immense waves coming from the ocean. These were thought to be legends, but they were actually accounts. From Japanese written sources, along with the oral histories of Native Americans, we now know with reasonable certainty that on the evening of January 26, 1700, one of the largest earthquakes the world has ever seen occurred along the western coast of North America. The Cascadia subduction zone ruptured along its entire length, producing tremendous shaking and enormous tsunamis that swept across the Pacific to Southeast Asia. The recognition of definitive evidence in geological records tells us that this was not a one-time event, but a disaster that has repeated many times at irregular intervals over hundreds of years. Geological evidence indicates that in the last 10,000 years, at least 41 major earthquakes have occurred in Cascadia. If you divide 10,000 by 41, you get 241, which is the recurrence interval for Cascadia, the average number of years between one earthquake and the next. This period is dangerous for two reasons. It's long enough to build an entire civilization on the worst fault line of a continent, and it's not long enough to forget about it. It's already been 315 years since the last event in a cycle with an average recurrence of 241 years, which is quite unsettling. Of course, recurrence intervals are based on average values, but recently geologists have predicted a 37% chance of a magnitude 8.2 event occurring within 50 years, and a 10 to 15% chance that the entire Cascadia subduction zone could collapse with a magnitude 9.2 event in the same time frame. In essence, the monster is just sleeping. There will come a time when the compressive movements of the plates become impossible to sustain statistically, and at that moment, the North American plate will spring back like a coil. After that, we can only imagine what will happen. An earthquake with a magnitude greater than 9 will shake the entire Pacific region, straddling the subduction zone. The coast will first experience seismic waves with magnitudes between 7 and 8. The entire northwestern edge of the continent, from California to Canada, will sink by at least 2 meters, or 6.6 feet, and shift 10 to 30 meters, 33 to 98 feet westward. This severe shaking will crumble older buildings, collapse bridges, cause landslides, and trigger soil liquefaction, a phenomenon where the ground turns almost liquid, destroying everything on it. Part of this displacement will occur underwater, moving a colossal amount of water. The resulting surface wave will rise, forming a large hill, then collapse. One side will rush westward towards Japan, while the other will head east, forming a liquid wall 1,000 kilometers or 621 miles long that will reach the northwest coast, on average 15 minutes after the earthquake begins, giving people very little time to flee to higher ground. The incoming waves could be 9 to 12 meters, 30 to 40 feet high, but some models suggest they could reach up to 30 meters or 98 feet, and in many parts of the coast, push up to 20 kilometers or 12 miles inland. In the northeastern Pacific, the impact area covers about 360,000 square kilometers, or 139,000 square miles, a region that includes major cities like Seattle, Tacoma, Portland, Eugene, Salem, the capital of Oregon, and Olympia, the capital of Washington State, home to approximately 7 million people. When the next major rupture occurs, this region will experience the worst natural disaster in North American history, outside of the 2010 Haiti earthquake, which caused over 100,000 deaths. At this point, the question always arises: with all the technology and science of recent decades, why haven't we been able to predict seismic monsters like megaquakes? The answer isn't simple. To date, scientists have not been able to accurately predict where and how an earthquake will occur, despite the high stakes. Estimates from the World Health Organization attribute about half of the deaths caused by natural disasters in the past 2 decades to earthquakes. Many geologists consider it nearly impossible to predict a seismic event precisely due to the extreme complexity of analyzing the entire Earth's crust. Others believe that new technologies, such as artificial intelligence, which can enhance predictive accuracy and speed, and smartphones, which can send instant notifications to people in danger, will help save many lives in the future. However, even the best technological efforts provide only a few seconds warning, minutes in rare cases, which is still too little time to evacuate. Experts admit that a future where our technology can accurately predict the location, timing, and intensity of a seismic event is far off. There's also the risk that incorrect predictions could cause more harm than good. The movement of tectonic plates that causes earthquakes happens very slowly, while ruptures occur instantaneously, leading to earthquakes that, without warning, cause chaos and destruction. Even the strongest recent quake, such as the 2010 Haiti earthquake, occurred without any warning. To avoid incorrect predictions, geologists have started to focus more on calculating the probabilities of a seismic event occurring rather than trying to predict individual quakes. Scientists use geological measurements, seismometer data, and historical records to identify high-risk areas. Through statistical models, they can estimate the likelihood of an earthquake occurring in the future. But this is of limited use. No one would leave their home just because they were told an earthquake might happen in 20 years. If that were the case, California would have been uninhabited long ago. In the 1970s and 80s, research focused on identifying signals that precede a seismic event, drawing from a mix of clues that included animal behavior, radon emissions, and possible changes in electromagnetic fields. Occasionally, some results were achieved, but nothing that could gain the approval of the scientific community. In the 1980s, scientists became convinced that a segment of the San Andreas Fault near Parkville, California, had expired for an earthquake. They analyzed heaps of historical data to pinpoint an exact date. They decided that the next quake would occur in 1993, but it didn't happen until 2004, when it struck Central California without any warning. This error sounded like a death knell for earthquake prediction. From that moment, many scientists shifted towards statistical models and probability calculations, moving away from a weather-like prediction approach. With technological advancements, however, there have been developments in early warning systems. These networks use seismographs to detect and assess the initial tremors, sending an alarm signal directly to people, giving them a few seconds' notice before the earthquake hits. For example, Shake Alert is a system that can send a message to users' phone with a warning ranging from 20 seconds to a minute before the quake arrives. The data comes from sensors and active seismograph stations, which measure the intensity of ground vibrations. When these sensors detect an incoming earthquake, computers can calculate the direction of the seismic wave within 5 seconds. Phone companies can then broadcast the alarm notification to users in the area. This system works because both internet signals and cellular networks travel at the speed of light, much faster than a seismic wave can move through the ground. Providing more than just a few seconds warning is a much more challenging task, according to many experts. Predicting an earthquake accurately requires detailed mapping and analysis of the Earth's crust to indicate where the likelihood of rupture is highest. Experts also emphasize the element of absolute randomness in the timing of an earthquake, which can sometimes occur without any warning. While technology gives us hope for improvement, many fear that without the necessary scientific rigor, a failure of these new systems could generate distrust in the technology itself. Researchers are now focusing on artificial intelligence and machine learning software, capable of handling vast amounts of data and identifying trends and patterns. The hope is that faster analysis than human capability will help scientists understand what happens before a seismic event, allowing them to identify potential warning signs. For example, some are developing nowcasting models, or very short-term forecasting, inspired by how the Federal Reserve makes predictions about the health of the U.S. economy. Scientists feed large amounts of data into machine learning software, from seismographic measurements to radar indications of surface deformations, to improve the ability to hypothesize where and when the next earthquake will occur. Even with technological improvements, it is unlikely that we will ever achieve exceptional precision. At best, in a few years, scientists might be able to predict the location of an earthquake within an area of about 1,000 kilometers by 1,000 kilometers, or 621 miles by 621 miles, with an approximation of 4 or 5 years. Expecting a higher level of detail is currently unrealistic because we do not have a satisfactory amount of data on past earthquakes. We have digital seismic data for only the last 25 to 30 years. Everything that happened before is either missing or highly incomplete. The hope is that the Cascadia Megaquake will not occur soon, before science has found an efficient predictive method. Otherwise, no matter how well prepared we are in terms of land management, the consequences will be terrible.